Seminar, the second lecture of this. Welcome everybody to the second pre-seminar and the second lecture series. So this week we have visiting from the UK, we have Jan Grabowski, and he will give the pre-seminar and the seminar. We'll start the pre-seminar, which is a brief introduction to cluster algebras and their quantum analogues.
Thank you. Thank you very much for the invitation and chance to talk. So I'm going to use the pre-seminar to go through particularly a kind of a worked example a bit more slowly than I'll have chance to in the main seminar. And I'm quite happy for this to be interactive. Stop me when things are confusing. Should also say that with the abstract that I put in, so on the group webpage, there should be a link to the notes that I'm drawing on for these. So if you want to know more stuff, there's more stuff there. Okay, what are we going to talk about? We're going to talk about cluster algebras and their quantum analogues. So I'm going to, because I've got plenty of board space, I'm going to try a sort of two-column approach. So commutative over this side to begin with, and then quantum shortly over there as well, and just sort of see how the two things line up against each other. So what are cluster algebras? Well, in particular, they're commutative algebras. So kind of all the things you might like about commutative algebras, knock yourself out. But they're defined in an unusual way. So they're defined by an iterative process. So rather than being defined axiomatically, this is the class of algebras I want, and it has these properties. You start with some input data, and then you do some operation on this input data, and this produces you an algebra. So this is a bit weird. What this effectively gives you is presentations for your algebra, but presentations of an unusual sort. So presentations with very many generators, but relatively simple relations. So there's some sort of trade-off where you exchange control over the relations, which is often the thing where you perhaps would have more control. You say, well, okay, if I want to kind of control those relations a bit more, I'm just going to have more generators in order to make this work. And this looks a bit funny. It looks a bit funny because it's sort of somehow the opposite end of the spectrum to what you get with, say, finite groups. So finite group theorists, there's a cohort post-classification, it's a cohort of finite group theorists working on presentations of groups, particularly wanting to compute effectively inside those groups. And the goal there is very often to find presentations with minimal numbers of generators, and consequently you end up with complicated relations. So you can show, remember this rightly, every finite simple group is 2 generator, I think, but the relations just get horrible. Maybe some of the very worst ones are 3. The vast majority at least are 2, I think. But cluster algebras are really somehow the other end of the spectrum. You can see we have loads of generators, but what we gain is control over the relations in some ways. What about quantum cluster algebras? Well, unsurprisingly, they're not going to be commutative anymore. There's almost a slight lie in the sense that you'll see as we go through that somehow drawing a distinction between these two classes isn't quite right. You should just absorb these into the quantum ones. But for pedagogical reasons, let's pretend they're massively different things. Mildly, and if you want me to say what I mean by mildly, I can. Probably later, but at some point I can say what I mean by mildly. They're non-commutative. but I'll just write iterative for as a shorthand for defined by an iterative process. So same mechanism produces you quantum version as the commutative version. What else? Oh yeah. The next bit is just verbatim true. There's still presentations with lots of generators and not less complicated relations. But the things I want to emphasize are very closely linked to their commutative counterparts. So this is a slogan, not, it's almost a theorem. I can make it slightly more precise if you like, but give or take, unusually for quantum algebras, Q equals 1 just literally works. Take the thing you've got, set Q equals 1, everything is good. That's unusual in this regime. They're generally very well behaved as quantum algebras, in the sense that if you look at the sorts of things that generally cause people headaches for quantum algebra, non-commutative geometry, it's often sort of cohomological dimensions, that sort of thing. So, perhaps things like GK dimension is a thing you might care about. If you don't know what GK dimension is, don't worry, go find Kirillov dimension. But this is some nice number you should be able to assign to your algebra, and it gives you good information. And just say easy, right? In the sense that once I've told you what your quantum cluster algebra is, I know instantly what its GK dimension is, and I'll show you that. So some of the ring theoretic properties turn out to be very straightforward. So amongst the class of all quantizations of things, these are particularly nice. Perhaps the other sort of implicit point to make there is that they include lots of well-known and important examples. Mostly examples coming from Lie theory in some sense or another. So things that are associated with quantum groups in the sense of quantized enveloping algebras, quantum coordinate rings, so UQGs, OQGs, flag varieties and things, Grassmannians. So that collection of Lie theoretic stuff, almost all of those are known to have this quantum cluster structure. So there's a big collection of examples out there, and they're things that other people care about for other reasons. So that's encouraging. Right. So that's kind of top highest level sketch. So I'll be a bit more detailed about what is actually what makes up a cluster algebra and a quantum cluster algebra. That does not make up a quantum cluster algebra. This is not one I prepared earlier. That's okay. Oh, if my board cleaning is incompetent, that's because I'm British. We don't do this anymore. We never did this, and we certainly don't do it anymore. Right. So cluster algebras. And really, I should say of geometric type. The honest answer is nobody studies the ones that aren't of geometric type anyway, so it doesn't really matter. Right, so we know it's commutative algebra. You probably at some point should ask me a question about what sort of field am I working over. For the purposes of today, any, so any field, could be complex numbers. If you like the complex numbers, that's the usual thing to do in undergraduate class. Or you could take Z. Yeah, I know it's not a field, but for these purposes, it may as well be. Doesn't really matter. You can do everything integrally, actually, which is why the field really doesn't matter. It doesn't matter very much. There will be an exclusion of roots of unity for a Q somewhere, but even that's only a bit of a technicality, really. So what do you need? You need initial data. So your initial data is Q, some quiver. If I say quiver, do people know what I mean by a quiver? No. Okay, that's fine. Just a directed graph. So I'm going to number the vertices. So yeah. For the purpose of today's talk, a finite graph, but see elsewhere. Collection of vertices and some arrows between them. The only conditions we make, at least for today, are no loops. So no arrow returning to the same vertex and no two cycles, no oriented two cycles. So you don't have the configuration of there and back, but sort of exclude those for reasons of making life slightly more sane. But yeah, then you get a quiver. In the quantum world, so do I have multiple edges? Yes, you can have multiple edges. So as long as I don't get oriented two cycles, I can have so the quiver with two vertices and two arrows going from 1 to 2, or 3 arrows going from 1 to 2. They're all legitimate. There is a version where you put weights on the arrows instead. It's essentially equivalent, modulo bit of technicality. I'm going to stick to the unweighted version. That's sort of what geometric type means here. The same geometric type, I'm also going to, because I'm going to do it with quivers, I'm going to think of doing skew, equivalently, you could write this down as a skew symmetric matrix. So a matrix, the matrix for this would look like, so a 1 where there's an arrow from 1 to 2, there's an arrow from 1 to 3, I'll make it skew symmetric. So skew symmetric integer matrices would sort of correspond, and you can relax that slightly to skew symmetrizable, so you end up with some sort of like non-simply laced type examples as well. But today I'm going to stick to skew symmetric because it's just a little bit easier. So that's my initial input data, is that quiver, or part of the initial input data. In the case of the quantum case, it's 2 quivers. For the purposes of this sort of worked example, it would be fine to take the same one twice. So just 2 quivers. I should say they should be on the same vertex set, the 2 arrangements of arrows on the same vertex set. Yeah, really sort of 2 skew symmetric matrices. So one is going to encode some stuff and the other is going to encode some other stuff. I'll tell you what stuff they're going to encode in a minute. The initial, so these are called cluster variables. So the initial variables are a collection of elements, say x1 up to xr, and you imagine them sort of living in the field of fractions, the corresponding rational function ring. So just some algebraically independent generators, just pick some. Over here, that's not quite true. You pick x1, xr contained in skew field of fractions. Of a quantum torus determined, so I should have said this quiver I call B and this one I call L, and this one over here I just have a B. So quantum torus determined by L. What do I mean by that? Well, I just mean that we have quasi-commutation relations. So xi times xj is q to the lij by xj xi. So in this, amongst this collection of variables I choose at the start, they no longer commute, because I'm not in commutative algebra, but they now quasi-commute, and the quasi-commutation is determined by this second bit of data that I pick. So that's what the extra data is for. And it will turn out eventually that my cluster algebra is some subalgebra of this ring of fractions. And similarly, the quantum cluster algebra is a particular subalgebra of this skew field of fractions of the quantum torus. So actually, that's maybe a good point to say that because of that, because everything is going to live in this skew field of fractions, and this is a collection of algebraically independent elements, so that this is where the ring theory is easy. The Gelfand-Kill dimension is going to be exactly this number R, which I call the rank of my cluster algebra. So some ring theoretic stuff I get to read off straight away just by construction. Yeah, R is the number of vertices. It's the number of variables. There's one variable per vertex. So what I will do when I get to the example, which I should start very shortly, is I will just write the variables in place of the quiver vertices, because that is more convenient. And then what do we do? I'm going to jump to the example actually, because there's not a lot more to say that I haven't already said.
So can you say how B enters here in the
Right. So that's the thing I should say before I move on. So B determines the recurrence. ... What does that mean? Well, you'll see in a second. Right, I'll go over to these words. Which of the colors is most visible? Any guesses? Is red likely to be okay? That's not going to stand out. No, because it looks like white on. No, that's not good. Let's try the blue one. Right, that's I just want something that's distinguishable. Good. Okay, so let's do everything over C to avoid any sort of, well, to avoid excessive amounts of lying about algebraic geometry. There's always a bit, but let's not do too much. So if I take 2 by 2 matrices with complex entries, to think of that as an affine space. So its coordinate ring is just a polynomial ring in 4 variables. So coordinate ring of M22 is just a polynomial algebra in the 4 sort of matrix entry elements. Okay. So I'm going to take as my initial cluster I'm going to take x11, take x12, I'm going to take x21, and I'm going to take delta, where delta is the thing you would expect, that's a determinant. I'm going to put this arrow in here, and I'm going to put some boxes around these 3. So in cluster algebra world, your variables come in two types. So some of them are mutable, meaning you can mutate there, and some of them are frozen, meaning you're not supposed to mutate there. So you do this iterative process that's determined by your matrix B only in the place where you're not frozen, and the frozenness is indicated by these boxes. So we're not going to mutate there. There's only one place we can mutate. And this quiver tells me what I'm supposed to do. So what I do, I replace x11 by something determined by this arrangement of things. I replace it by mu sub x11 of x11. And the relation is this one, that this new element I get times the old one is a sum of two monomials, and I form the two monomials from ins and outs. So I take the monomial form by taking the product of all the things on the way in. So what comes into this vertex? Well, just delta does. And then my other monomial is all the things that go out. I'm in commutative world still, temporarily at least. So it doesn't matter what order I write those down in, and we're all happy. And then you can check that if I expand this out, by substituting this definition, we see that it implies that my new thing that I get, my mutated element, is actually just the element x22. So this turns out to be a cluster algebra with two clusters. So it's actually a type A1 cluster algebra. There are two clusters. There's one that looks like x11, x12, delta, x21. And there's an involutive mutation operation, so I can mutate back the other way as well. And all it does is it swaps out my x11 for my x22. Everything else stays unchanged. And the cluster algebra associated with this data is the thing that's generated then by all of the things I get under iterated mutation. So this will be the stuff that was in my first one and stuff I get under mutation. In principle, ... but in practice, in this case, that doesn't happen. This process terminates, so a finite type thing. And so it just turns out to be that. And so, of course, this generates all of M22. So you can see we've taken a 4-generator polynomial ring and generated it by 5 things. So, yay, well done. Good for us. Uh-huh. Mm-hmm.
So the boxes are an extra piece of data.
Yeah, it turns out in the geometric examples that you tend to get these frozen vertices that sit in every cluster.
It's not about the initial data. I mean, where did they come from?
Yeah, so perhaps that there probably ideally ought to have been another line in here that says you can declare that some of them are frozen or not. So there are cluster algebras without frozen variables, and there are cluster algebras with frozen variables. So yes, when you make this choice, you make some subdivision into mutable and frozen. And frozen means you don't mutate there. Yeah, it's an extra nuance that turns up in the examples. Now, in the remaining 4 minutes, I shall magically before your eyes quantize this whole situation. If that doesn't impress you, then nothing will. Yes.
So you write down the graph, which is B, and then you have this mu. Do you get the mu from the graph, or is that another piece of data?
So the this graph determines this relation. So let me write down a more general looking formula. So if I take my quiver Q and I write down the skew symmetric matrix skew symmetric integer matrix B, just so that I've got numbers. And then the general form of the relation, so every exchange relation, so every mutation relation, these are called exchange relations. Every relation is this, not quadratic is the wrong word, but it's the product of an old thing and a new thing equals a sum of two monomials. Every relation looks like that. And so it looks like mu of at some vertex k of the kth thing multiplied by, so this is old multiplied by new. I mean, if you want to divide through by xk, then feel free. But it sort of looks slightly neater. And again, I say it's if I use as a shorthand, j goes to I, this means, so j goes to k, this is all a product over all the variables that where the arrows go into this kth one. So I take the product of all of those. Oh, sorry. Yeah, x. Yes, I take, these are big x's, so can never decide whether to use small ones or big ones. I should be using big ones. To the relevant power, just, so I count the number of arrows coming in. So if there are multiple arrows from the same vertex, I count them with multiplicity. And then this one is arrows going out. Yeah, so actually, this would be, these would correspond to the BJK pluses, and these would correspond to BJK minuses. So the skew symmetric matrix has some, if I look down any column, some entries are positive and some entries are negative, corresponding to in versus out. So I take the positive ones and the negative ones. It's the other way of looking at it. So this corresponded to arrows in, and this monomial was arrows out. Yeah.
Okay, and then you
do the same thing again. You keep doing the same thing. You go,
add the new relation.
in particular, yes. So there is a new graph. In this case, I wrote down the wrong graph. I'll now correct it. The arrows magically change around for reasons that there is a general formula which tells you how to change the graph. Usually more complicated things happen. But yes, you then also you change the quiver or the graph according to a set of rules as well, which look a lot less pretty to write down. And you get a new graph, and then you look at the other places you can mutate, and you just keep going. You kind of expand out through a big k-ary or n-ary tree, however many mutations you can do, and you just keep going until you stop. Sometimes you never stop. So for some cluster algebras, this process just keeps on going. You just keep getting more and more variables, but that's okay. You just take them all, some suitably defined sense.
No, sorry.
Mhm.
This delta, I mean, the delta is x1 and x2, 1 and 6. Where did that come from? Because that's not apparent in the graph.
No, I'm telling you a choice that works. So I'm saying choose these elements, and this will give me a presentation that will have these nice properties. Why is this the right thing to do? Well, in some sense, if I wanted a relation like this one to hold, the only thing that would involving the x, so let's say I wanted to try to get all the xij's out at the end, I would need things like this. No, so when you form a cluster algebra structure on your given ring, the hardest bit is to work out which elements to choose and what graph to associate with it. And then you have to prove that everything works. That's not trivial. So this is not automatic from anything. It was worked out that this was the right thing to do. Yes.
Descriptions of the set.
Yes. Of different ranks, of different types. So the 2,4 Grassmannian is example way back in Fermi-Zelevinsky, the original paper that defined these things. It admits a type A cluster algebra structure, which is the one associated with the sort of usual Grassmannian presentation, and a type B cluster structure, possibly of the same rank in that case, but different Dynkin type, so different combinatorics. So the mutation combinatorics can be different in the same algebra. So it's a very much a choice of presentation for your algebra. It's not an invariant of the algebra at all. Yeah, strongly not an invariant.
The x1, xr
Mhm.
in this example are x11, x12, x21, and delta,
Yes.
right? And they're not free, like they already have delta already is made up of the other ones. Like they're already start with a bunch of relations.
Yeah, so this is a subtle shift from on this side, making an abstract cluster algebra from some choice of initial data, to over here, finding a cluster algebra structure in some algebra I already know. Yeah, that's the distinction. Yeah, so if I'm going to do the latter, if I'm going to find a cluster structure on something I know, then I've got to identify the right collection of elements, and I've got to show that they have the exchange relations that I would expect. Right. I do want to show you the quantization. I'm going to have to be a bit sketchier than I was going to be, but that's okay. Don't worry about it. OQ M22. Okay, this is no longer true. You do something else. Yeah, there is a presentation for that algebra. And either you know it or you don't. It doesn't really matter for the purposes of what I'm going to do. Let's just take the quantization of it. Well, what do I need to tweak over here? I should have an extra Q appearing in delta. So I take the quantum determinant rather than just delta. There are still these coordinate functions, even though they're the quantized versions. I'm not going to write down. So this is some algebra generated by xij's modulo some more complicated relations. I'm not going to attach q's to them because I somehow don't need to. But this is now the quantum determinant. The extra data, the L data, I'll write it down as a matrix. It describes the quasi-commutation of these four things I've chosen. So it is true that x11 quasi-commutes with x12, x11 quasi-commutes with x21, and actually honestly commutes with the quantum determinant, which is central. I'm very close to telling you the relations of this algebra actually at that point. And so what do I need to do when I do the rest? What I didn't say here, but I should have done, that these two things have to have some sort of compatibility relationship between them. I can't just take two arbitrary things, they have to have some nice property. This property essentially is B and L are nearly, it's not strictly true, but it's not far off true. They're sort of dual to each other. So you have to make some suitable choice. If you do make that suitable choice, and this is a suitable choice, then it turns out that the relation is just, let's see. I'll leave that one there for comparison. I'm going to write the quantum relation here. I'm going to write it in a slightly different form that's slightly better adapted. So the quantum relation, quantum exchange relation, is that mu of x11 is x11 inverse. So we knew we were going to divide through by the x11 times delta q plus q times x11 inverse times x12, x21. And again, by a bit of manipulating relations and magic, this does give me x22. So the slogan is you can put the q's in the right place and it still works. So what you might observe as well is this justification of this comment that q equals 1 works. if I literally write Q equals 1, neither delta Q nor this relation collapses. I don't get any annoying Q minus Q inverses that I'm dividing by or anything else. There are theorems that say that the relations I get, the expressions I get, turn out to have nice sort of positivity properties that essentially force that I can take the Q equals 1 version of my quantum cluster algebra, and it will give me a commutative one. So I'll say more about this in the main talk, but this is sort of the beginning of the idea that quantum cluster algebras are a different way to quantize ordinary commutative ones, and this quantization is really very close. Normally quantization is quite complicated, not necessarily easy to construct, but so I will say a bit more, but in some sense you can see you just need a little bit of extra data and then you can quantize. So it gives you a slightly different approach to things. Yeah, but the point of what I was trying to say here was just to familiarize you with some of the words. And I'll talk a bit about this example as well in the main talk, but I'll stop there.
So do we have some quick questions?
What does that mean again?
Oh, so commute up to a power of Q. So A times B is Q to the something B times A. So you've got to be a little bit careful. What happens in quantum cluster algebras is that each cluster, each of these special collections of elements have quasi-commutation in them. So you have loads and loads of different quantum tori. So in the classical situation, each cluster really corresponds to a torus, and you glue all these tori together using these relations. In the quantum setting, you get lots of different quantum tori, and you glue them together. So it's not true that anything quasi-commutes with anything else. You can break that very easily by adding two things that quasi-commute with different powers. So it's not true that everything in the algebra or that every quantum cluster variable quasi-commutes with every other one. But within a given cluster, these are distinguished sets. And one thing that distinguishes them is that they form a quantum torus together.
So in this example here of the quantum matrices, you're just looking at columns or rows would be your two clusters. So in the first column and the second column, they Q commute.
Yes.
And then you glue them together, and that's what's going to give you the determinant relation in the
Yes.
Messier.
Yes. So yeah, there's some in this very small example, it's true that the birational map that glues the two tori is just the determinant, but it gets much more complicated. Even if I went to 2x3 matrices, you'd already start to see some other stuff coming in and out. But you can do this. So you can do this construction for arbitrary matrix. So M and N size quantum matrices. That's been known for a long time.
Presentation, if you have two different presentations of the same classical guy and you quantize both, you can get different non-isomorphic algebra.
Well, that's a good question. Almost certainly yes.
But sometimes
I don't know either an example or a counterexample. So cluster theorists tend to take the point of view of fixing a cluster structure at the start and then asking stuff about it.
yeah.
There's a whole other talk, but it's very hard to talk about morphisms between different cluster algebras. The categories, attempts at constructing a category of cluster algebras have not really succeeded because, but for the basic reason that I said at the start, if I take two groups, I know what category to take. It's group homomorphisms between them. If I take two groups, each equipped with a presentation, that's not good categorically. So same problem. Defining morphisms of cluster algebras is hard. Even defining isomorphism of cluster algebra, there are three different levels, and it's not clear which one you want. And yeah, everything that could go wrong does go wrong. There's sort of injections, but they're a bit funny. and quotients are horrible. There's no ideals. There's no cluster ideals. So you can't do quotients. It's like the category of rings, but worse. So end on a happy note.
Maybe that's.
Quick question.
So I guess that in some cases, your cluster algebra might also have a coproduct or an antipode. Is there some way to see this via the B and the L, or is it just you're lucky sometimes and sometimes not?
So Ray and I were talking about this earlier today. Nobody has really studied this. Nobody's really looked at cluster algebras or quantum cluster algebras from the sort of Hopf-Co point of view. There are examples I know where those algebras do admit coproducts or co-module structures or all that stuff. But yeah, I'm probably the best person to ask what's known. And as far as I'm aware, nothing is known. And I've not even tried really to do the calculations very much. On the one hand, here, this feels like a very obvious question for everybody to ask. Somehow out in cluster community, the focus has been on other things. Yeah. There were lots of open questions of that sort. Is there anything obvious to say? The only thing I will say is, because lots of these examples come from quantum groups, there must be more than we're currently understanding. Yeah. Ask me again at the end of the main talk.
Okay, I will do it.
Yeah, so at least I know what's coming. I've got an hour to think about it.
Okay, there I think we should stop so we can start the other seminar on time. So we'll thank you.